In 9.4, we're going to move on to more series and sequences. We've had a pretty in-depth study of arithmetic and geometric, but now we're going to look at new patterns that do not fit those molds. So in this section, what we are going to have to do is, just like for our arithmetic series formula, we came up with that a sub n plus a sub 1, so the first term plus the last term, times how many terms divided by 2. And we kind of had a non-wordy proof of why that worked. So now we're going to use what we call is a proof of induction. We're going to use that type of proof to prove some of the series formulas that we come up with for the sequences that we have in this chapter. So also we're going to put the formulas we have proven to use. And we're actually going to do this in the opposite way. First we're going to put these formulas to use, and then we're going to prove why they work. Alright, so if you would, this is a warm-up, and what you need to do is write the explicit sequence for the following patterns. And just as a reminder, an example of an explicit sequence would be something like a sub n is equal to d times n plus c. We use this for an arithmetic sequence. It was a rigid way of coming up with a relationship between a position and then a position in a sequence and what term was in that position, right? So if you wanted a sub 10, plug in 10, and then you would get what was in that sequence. So also we had a sub n is equal to, and then a sub 1 times r to the n minus 1, and that was if we had geometric. So go ahead, some of these may or may not fit those molds. Try to come up with the explicit sequences for these patterns down here. Alright, so after giving this a try, I am going to expose the answers now, so if you want more time, pause me. But what I do want you to see for this one is this one does have a common difference. What you'll notice is we're trying to figure out, is there something being added each time over and over again? So if you will notice, we're adding just one over and over again. So this will fit an arithmetic sequence, and we could come up with something like a sub n is equal to 1, because that's our difference, n plus, and we need to go one term back to find our 0th term, or what our y-intercept would be. So in this case, if we went back 1, we would subtract 1 from this term, and we would get 0. So there we have it. What you will notice in this section is a lot of the times we don't use n anymore. For the index value, we'll use something like this. A sub I is equal to 1 times I, so I'm just going to write I. And you can see how, hey, yeah, this totally works. Plug in, any position that you're interested in, and you're going to get that correct value. So a sub 1 is just 1, a sub 2 is just 2. So the index value, or the position value, ends up being the term itself. So very, very basic line equation. Same thing down here. What you will notice is these are neither arithmetic or geometric. You could simplify these down here, and what you would be ending up finding is there's no common difference that you're adding each time to get from one term to the next. And then there's also no ratio, like in the geometric types of sequences that we had, where you're multiplying some sort of constant ratio to get from one term to the next. So none of these will work, but what you should notice is, just like up here, is in the index value. This is a sub 1, a sub 2, a sub 3. This index value, or where we are in our sequence, our third place or third position, it's going to be present in the term, right? So here a sub 4 is going to be that 4 squared. So what could represent this for us is a sub j is equal to j squared, right? That will work for any one. And then same thing down here, a sub I is equal to I cubed. So what we are getting into are power series, or sequences that are just powers, and so this would be what we could call maybe the sequence of power of 1, or power of 2, power of 3. Alright, so now if we were to take those very warm-ups from the previous slide and add them all up, what we are then going to have to use is our sigma notation. So if you would notice, here we have those same sequence, explicit sequence equations that we came up with, and now what we're just doing is we're summing them up. So, oh, I'm sorry, I meant to sum these up. So if we're going to sum these up, what we would have to do is just use sigma notation. And you could see, yeah, if you went up to the end of the second, so the end to the second term, you can see that, hey, yeah, starting at index 1, we would have 1 squared plus 2 squared plus dot 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 all the way up until the nth squared. And then same thing down here. So what we are going to do is, unlike with the arithmetic series formula that you came up with, again it was that first term plus the last term times the number of terms divided by 2, this time I'm going to give you those formulas. So note you could either use something like this, but this is the more common way or more common formula that we end up using. So here is a power of 1. How would you come up with the total of the power of 1 sequence and summing them up? Well, you could just use this formula right here. Same thing with this, we use that and we use this. These come in a lot of handy in calculus. And then just a quick reminder, we went over these in the 9.1 video, so take a look at those again if you want, but we have some properties that we can go by when we're talking about summation notation. So for example, if we had something like this, starting at the first value all the way up until the third, if we were trying to sum up a sequence that was just a constant, then it's going to look something like this. A sub 1 would just be, well, 5, because that's what our sequence is defined as. And then plus a sub 2, well, that would just be 5 as well, plus 5. So however many terms there are, well, there are 3, we would multiply by whatever that constant was. Okay, so I'm not going to go into proving these because we did those in 9.1. Oh, and sorry, here's the sum and difference, where if you have 2 different sequences separated by addition or subtraction, you can actually just sum up each one of those sequences individually. Alright, so let's put this to use. Your example number 25, this is from your homework. So what you will note is I have kind of collected the new power series formulas, and then we also have our old properties. So the first thing that I'm going to do is I'm actually going to notice that I have the sum and difference formula going on. So that's this right here. And by the way, if worst came to worst, what you would be stuck doing is you would just have to say, alright, starting at the value 1, I'm going to plug in a sub 1. It's going to be 1 squared minus 1. And then plus a sub 2, it would be 2 squared minus 2 plus 3 squared minus 3 plus 4 squared dot dot dot. Okay, you could do that and then add up every single one of those. But what we can also do is use these properties and formulas to help us through. So I'm going to use this right now, and I'm just going to individually look at these two terms separated by a subtraction sign, and we are going from n equals 1 all the way up to 6, and n equals 1 all the way up to 6. Same sigma sign that I've to a point distributed to each one of those terms, but not really, because you can't really distribute something that's not a number. Okay, so anyway, this is what we have. So now what we'll want to recognize is that you're trying to take the sum of a sequence that's a power of 2. So this is when we can use this right here. So keep in mind we don't have the same letters, but as long as these line up, then we know that that's what we're plugging in. 1, 2, 3. So it is this type of formula all the way up to 6. So what you could do here is you could just say, all right, we need to use this formula. So 2 times n cubed plus 3n squared plus n all over 6. But we know what that n was. We weren't just going up to anything. We were going up to 6 specifically. So we have 2 times 6 cubed plus 3 times 6 squared plus 6 all over 6. And then we have minus. This one right here is just a power of 1. This was also arithmetic, but it also fits this power of 1. So either way, you can't go wrong. This one has a couple of different formulas that we have. This one's going to be n squared plus n all over 2. It's a sum of a power of 1 sequence. So here, though, we do know our n's. So it's 6 squared plus 6 all over 2. When we do this, if you type that into your calculator, you are going to get 91 minus, type this into your calculator, you're going to get 21 for a total answer of 70. You would have gotten the same thing adding them all up, but here we use some formulas and properties, and we were able to get a sound answer as well. So now what we're going to do is head into proving these series formulas that we have now worked with. So where do they come from? How can they work? So again, you can use the various proofs that we've had in the past. Like I used the rectangle one where you would draw bars to represent the sequences and then create another one, flip it, and then you would have a rectangle, and that proved our arithmetic series. Now what we're going to do is a mathematical induction proof, and basically if you make one domino solid to hit the next and you show that each one of those is kind of in the same setup, you'll see that yeah, they're all going to hit each other and fall into them. So another way to look at this, I found this online, so go ahead and read through this. But another way to kind of visualize this is if you can say that the first basis of a formula is solid and it works, and you assume that any kind of integer is going to work for your formula, then as long as you can prove the next integer will work, then you've proven that they'll all will work. This thing will go on forever no matter what integer you plug in. So it's a little bit confusing, but here are the steps that you're going to want to write down. I'm sorry, you gotta fix this to be K. Alright, so here are my steps still, and this is number 5 from your homework. So what I want you to see is, first of all, what are we trying to prove here? Well, this is the sequence just 2n, and since we do know that we're going up until n, what I am going to do is use the sigma sign since we're adding up and go up to n, which means I'm going to have to choose a different index number, so I'm just going to choose I to stand for the position that we have interest in. So we're starting with the first term, and here is technically our equation. You could come up with it if we wanted to, but you can see that's what we're doing. Whatever position you have, you're just multiplying by 2. So a sub 1 would be 2 times 1, and we would nail that. 2 times 2, and so on. And what we're trying to prove here is you can use the formula. Instead, if I had 10 here, instead of individually doing a sub 1 and adding up to a sub 10, what you could just use is 10 times 10 plus 1. Alright, so we got to prove that this is going to work. Alright, so to do this, in step 1, what we must prove is that it actually works for our most basic number, 1. So let's go ahead. Step 1, what we need to show is that let n equal 1, and what we're going to see is, does it work? So I'm going to plug in 1 for my n, so we're summing from the index number 1 just up until 1 of this 2i, and then what we want to show is that let n equal 1, so 1 times 1 plus 1. So if you were to look at this, say, alright, we're just going from 1 to 1, so just 1. We have 2 times 1 is what the sigma would represent. So it was the very basic summation of just the first term. And then what you have over here is 1 times 2. So what we have just shown is, yeah, this thing works if we're just at the basic step of doing just one term, or the first term. So use this, thus true, so thus true for n equals 1. We've proven the most basic truth, and now what we're going to do is proceed to then assume that it's going to work for any integer, and as long as we can show that it works for any integer plus the next, we've shown the domino effect that this will continue on forever. So step 2, this is going to, we're going to start with assume equation is true, or this formula is true for n equals k, where k is any integer. I'm just going to write int. So what I am going to do then is assume, what we are assuming is let n be k, and then I still equals, we're starting still at 1 of 2i, and then therefore this is going to work k times k plus 1. So we let our k, or I'm sorry, our n be k. So I know it's kind of weird. We let n be another variable, but we're opening this up for k to be any variable, any number. So now that we've assumed this, what we need to show, n equals k plus 1 is true. So now what we're going to do is use this very same thing. We need to show that if we went up to k plus 1, not just k, so starting at index or position 1 of this 2i, that it's going to actually work that k plus 1 would also, if we went up to k plus 1, we could also put k plus 1 in for these k's. So we need to show this. It's a little bit weird. Look at it for a second after I do this. But we're going to have k plus 1 plus 1. So if it worked for k, we need to show that it's going to work for the next term after k. So here I am going to simplify this as equal to k plus 1 times k plus 2. So k plus 1 times k plus 2. And when you simplify that completely, it's just k squared plus 3k plus 2. Alright, so we need to show that this is equal to this. Alright, and in step 3, we're going to use this right here, and again, sorry, I had a typo, this should be k. So what we're going to use is the concept of, well, the summation of k plus 1 would be the summation of k plus an extra a sub k plus 1, right? Because the summation of this a sub n up until k would be a sub 1 plus a sub 2 plus a sub 3 plus a sub 4 all the way up until a sub k, but we need an extra plus a sub k plus 1 if we're going to go not from 1 to k, but 1 to k plus 1. So this right here is going to be a sub 1 plus a sub 2 plus a sub 3 plus dot 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 all the way up to a sub k, right? All the way up until an extra k plus 1. So you have to realize that a sub k plus 1, the summation from 1 to k plus 1, it's going to have embedded in it the summation from 1 to k. So here, what we're going to do in step 3 is we're going to let n equal k plus 1. And what we're going to show then is the summation of 2i starting at I equals 1 to k plus 1 is going to be equal to the summation starting at 1 of 2i up until k plus an extra a sub k plus 1. So we need to show that right now. So first of all, what we are going to use is our assumption. So I'm going to write this again. Sorry, I'm going so crooked. Equals. We're going to take this out and plug in our assumption that, yeah, because we were able to prove that bottom rung, we were able to assume that it's going to work for any integer. So instead of this thing right here, I'm going to plug in this k plus 1. So we have k times k plus 1, I meant, plus a sub k plus 1. So we still need to eventually wind up with this, right? So here, what I need you to consider then is this notation. If you go back though and understand that our sequence is equal to this a sub I, so we're just going to be plugging in k plus 1, right? So we have 2 times k plus 1 is what this thing equals right here. So now we have k times k plus 1 plus 2 times k plus 1, correct? So now distribute this and simplify, because again we're aiming to make it equal to this, and hopefully if we do work this out using our assumption and just using what our sequence was equal to, these are going to match up. So we have k squared plus k plus 2k plus, and then when I distribute that 2, it's going to be 2. And looky there, we have k squared plus 3k plus 2. So we have just proven that, yeah, the summation of this sequence from 1 to k plus 1 by using our assumption and just plugging into our summation, our sequence notation, we were able to prove what we needed to set out to prove as we stated in step 2. So step 4, you can say, thus, by mathematical induction. In steps 2 and 3, the formula is valid for all integers n greater than or equal to 1. We started with 1, we said it's going to work for then an integer, and then we proved that it's going to work for an integer plus the next one, so an integer and the next one. So any integer that you can have, the next one is going to hold true. There's your homework. So these ones right here are proofs by induction. The rest of them are the second objective, where you're just using the series formulas that you have come up with. So proofs by induction, I realize, are going to be a little bit hard, and we can bounce those off ideas in class, but otherwise you need to be able to use those summation properties, and then also the series, the power formulas of series.